Hello, Algebra 1 CP students. Hopefully you're having a good day so far. Today, I'd like to talk about our second category of compound inequalities, that being problems involving the word and as opposed to problems involving the word or. These problems are commonly called conjunctions as opposed to disjunctions from the other day. And in order for a compound inequality with and to be true, it needs the values for x that we choose need to satisfy both conditions. So, unlike with or, where we would be happy if either one of these were true or both, with and, we're really concerned with finding values for x that satisfy this and this at the same time. So we're going to be looking for some region of overlap between these two things. So we'll get there in just a moment. But just like the problems with or, in order to solve a compound inequality and graph it with and, we are going to start by just solving both inequalities separately. It still is pretty much two inequalities going on in the exact same problem and then just graph together. So we'll start with that and then see what we can do from there. In order to solve this inequality, should be very comfortable at this point. It's just one step. I would just add 5 to both sides. And we solve our first inequality by saying that x is less than or equal to 6. In order to solve my second inequality, I would multiply by -4 on both sides to undo the division by -4. Since we're multiplying by a negative value, it is going to cause that inequality sign to flip, and I'd be left with saying and x is greater than now -1 times -4, +4. Okay? So, think about what this statement is saying. The values for x that make this problem work have to be less than or equal to 6 and have to be greater than 4. All right, so think about what that means. That means they have to essentially be between 4 and 6, not including 4, but including 6. I think a good way to at least start by representing these things on a number line is just sort of think of them separately and then visualize which regions of the number line would be captured by both of these things. What do I mean by that? Well, what I mean is if I were to graph just the inequality of x is greater than 4, just that one by itself, right? Suppose 4 on my number line is, we'll say it's right here. We'll say that's 6. X is greater than 4 means I would have an open circle on 4, and I would be shading to the right like that, correct? Because that's everything greater than. Think about now just graphing the inequality of x is less than or equal to 6, right? If I'm focused just on that inequality now, if this is 4 and this is 6, that's going to be all the stuff from here, which would be a shaded in circle because it is less than or equal to, going now to the left, all the way over there. So the question is, looking at both of those inequalities, what values for x are satisfied or are captured by both of them? And hopefully you can see it would be the ones in between here, the ones that are between 4 and 6, because see, those are the ones that are highlighted and shaded in both of these number lines. Okay? So that's exactly what we would say here. Our real graph of this, x is less than or equal to 6 and x is greater than 4, would be kind of look like this. Suppose this is 4, and if so, this would be 6. It would be all the values that are in between the shading here, from 4 to 6. I would have my closed point at 6, I'd have my open point at 4, and I would shade in the stuff in between. It would look like that. Okay? Because that's the region of the number line that is satisfied by both this and this. It's the stuff that got caught in the middle of both shadings. All right, so that's what we're looking for when we're dealing with and problems. We're looking for parts of the number line that are satisfied by both of these things. Okie doke. Let's take a look at another problem, one that's a bit more difficult in terms of solving the actual inequality. Something like this. Ready? Another example. Let's do -3x minus 4 is less than 8 minus 6x. I want to find values for x that makes that true and also makes this true at the same time. 2x plus 3 is less than or equal to -2 plus 7x. Okay? Again, looks scary when you see that whole big thing written out, but really it's just two separate inequalities. And then we're going to see what parts of the graph are covered by both of these things. Let's take a look. Do the first one here. I would add 6x over to the other side because I have variables on both sides. We don't want to have variables on both sides. I only want those x's on one side. I add 6x. I get 3x minus 4 is less than 8. We've now reached a two-step inequality. We love two steps because in order to get x alone, we know exactly what to do here. We're going to have to get rid of everything else on the same side of the inequality, giving us that 3x is less than 8 plus 4, which is 12. And lastly, dividing both sides by 3 gives us that x is less than 4. Okay? So keep in mind that the values for x that will work out here are those that are less than 4 and also those that satisfy this. I will, just for the sake of doing it and getting all the variables on the left, I'll subtract 7x over to the left side. That gives us negative 5x plus 3 is less than or equal to negative 2. Again, the reason I'm going through these a little bit quickly at this point in terms of the solving is because we should be fairly comfortable with solving inequalities like this now, since we've done it for a long time. I would now get x alone by subtracting 3 from both sides, gives us negative 5x is less than or equal to negative 2 minus 3, negative 5. If you are having difficulty following these steps, though, I would definitely recommend going back to watching the initial videos on solving inequalities because I take this a lot slower. And maybe even going back to the solving equations as well, because it's really the same processes. Lastly, divide both sides by negative 5 to undo the multiplication of negative 5 times x. Since we're dividing by a negative, that inequality is going to flip and become x is greater than or equal to positive 1. So think about what this is saying. This is saying that your x values have to be less than 4 and have to be bigger than or equal to 1. All right, we don't have to do all these separate graphs. We can do this one on just one graph. Okay? And picture what I'm about to tell you. If x is, let's see, let's put 4 here. That means 3, 2, 1 would be right there. Okay? If x is less than 4, think about it. That would be all the stuff from 4 and going this way. Correct? Can you picture that? It would be from 4 with an open circle, and it would be trending to the left. It would be shaded to the left. If x is greater than or equal to 1, it would be a closed circle on 1, because it's included, and all of the stuff shaded to the right. So which region of the graph is covered by both of these cases? It would be the one right in the middle here. There'd be an open circle on 4, shaded this way, closed circle on 1, shaded this way. This region is covered by both. And it would look just like that. Okay? That is the part of the number line that is both less than 4 and greater than 1, or equal to 1. Hopefully that makes sense. All right. So just like with the OR problems, we're solving two inequalities and graphing them on the same number line, but now we're looking for that overlap because we need to satisfy the word and, talking about both cases. Okay? Now, what's cool about compound inequalities with and is they can actually be written without the word and. And you might be like, how can you write a and problem without the word and? Oh, let me show you. Something like this. If I had 17 is less than or equal to 7 minus 5x, which is less than 52. Ooh, look at that. Three pieces of this compound inequality, two inequality symbols in the same problem. How exciting. Well, pay attention to how I actually read this problem to you. I said 17 is less than or equal to 7 minus 5x, which is less than 52. So notice that this really is two inequalities in disguise, sort of sandwiched together. This 7 minus 5x is greater than or equal to 17, and also this 7 minus 5x is less than 52. So when you see an inequality sort of smushed together like this, what I would recommend is I'd recommend for Algebra 1 CP sort of break it apart and treat them separately, like up here. We can break this apart to say that 17 is less than or equal to 7 minus 5x. And we can also break this side apart to say, well, 7 minus 5x is less than 52. Do you see that? This first piece is like breaking apart this section, and this second piece is grouping together this second section. All right. Now, just like before, we can go ahead and solve each one separately. I would subtract 7 from both sides, giving me 10 is less than or equal to negative 5x. Divide both sides by negative 5, and notice we're dividing by a negative. That inequality is going to flip to be negative 2 is greater than or equal to x. All right. If you're uncomfortable with having your x on the right side of an inequality, notice if you read it from right to left, you could say x is less than or equal to negative 2. You can rewrite it that way if you so desire. Notice the inequality is still pointing to the bigger thing. Inequality still pointing to the bigger thing. Okay? Cool. Next problem over here is a little easier, a little more straightforward. Subtract 7 from both sides. We would get negative 5x is less than 52 minus 7 is 45. And lastly, divide both sides by negative 5. Divide by negative 5. We would get that x is greater than, notice the inequality flipped again because we divided by a negative. 45 divided by negative 5, negative 9. So think about it. The values that would work, the values for x that would work here, are those that are smaller than or equal to negative 2. We'll put that here. And bigger than 9, right? And bigger than 9. All right, bigger than negative 9, excuse me. And bigger than negative 9. Here's negative 3, 4, 5, 6, 7, 8, 9. Negative 9. So on a number line, think of what would be shaded in. It would be all the stuff from here going down, and all the stuff from here going up. So the regions of the number line that's caught in the middle, that's captured by both of these, is this section right here. Looks like that. Okay? Because all this stuff over here would only satisfy this, not this. All this stuff over here would only satisfy this and not this. Right? This stuff would not be greater than negative 9. It would be this, but not this. And this stuff over here would be this, not that. So that's why this region is what satisfies both. All right? So again, when you see this sort of smushed together inequality of both pieces at the same time, just split them up into two separate ones and solve like normal. Solve like normal. Okay? Let's do a couple more. One more of that. I want to show you one more of that sort of smushed together style. Ready? Something that looks like this. If I had, for example, negative x minus 10 is less than or equal to 2x plus 5, which is less than negative 3 minus 2x. Okay, putting a little more variables in there. Right? Again, it's sort of smushed together as one big statement, saying that this 2x plus 5 is greater than or equal to the negative x minus 10, and also this 2x plus 5 is less than the negative 3 minus 2x. It's right in the middle. Think of this as the smallest, this is in the middle, and this would be the biggest. Right? So let's break it apart and say, take our first little group here, negative x minus 10 is less than or equal to 2x plus 5. And our second group would be the second half. That 2x plus 5 is also less than negative 3 minus 2x. All right? And now we can just solve each one independently. I would say here for the first one, let's add x to both sides. Might as well, just to make everything positive. I get negative 10 is less than or equal to 3x plus 5. Two-step inequality. We love two-step inequalities. I would subtract 5 from both sides. We get negative 15 is less than or equal to 3x. Divide both sides by 3, and we're ending up with negative 5 is less than or equal to x, which again, if you read the inequality from right to left, you could rewrite, if you so desire, you don't have to, as x is greater than or equal to negative 5. X is greater than or equal to negative 5, right? If negative 5 is less than or equal to x, then therefore, x would be greater than or equal to negative 5. So you can sort of make that switch if you want. You don't have to, but if you want. Same thing over here. I'm going to solve this one as well. I'm going to add 2x to both sides to eliminate the minus 2x here. That gives me 4x plus 5 is less than negative 3. Now we can subtract 5 from both sides, giving us that 4x is less than negative 3 minus 5, negative 8. Let's divide both sides by the 4 to undo the multiplication by 4. And last but not least, no flip-flopping involved here at all. We get x is less than negative 2. Okay? So once again, I encourage you to think about all of the possible solutions. Think about the fact that we're looking for a part of the number line that's bigger than or equal to negative 5. Say if we put negative 5 here, and less than negative 2. Here's negative 2. Well, x is less than negative 2 would be an open circle on here and shading everywhere to the left. You could probably picture that. X is greater than or equal to negative 5 would be a closed circle on here and shading everywhere to the right. So the region that works out is the stuff that's right in the middle. That satisfies both. It's going to be open circle here, closed circle here, because here we have just a less than. Here we have a greater than or equal to. And then I shade all the stuff in the middle. Okay? Again, picture the fact that this first one would be open circle, shade. This one would be closed circle, shade. The region that's encompassed by both of them is this right here. Hopefully that makes sense. Okay. So that's pretty much graphing compound inequalities involving the word and. That's pretty much all there is to it. But what I want to show you, just to make sure we cover all of our special cases here, just like when we dealt with problems with or, where you can have all real numbers if the two or inequalities sort of crisscross each other, we can have the same thing happen with and, but instead of all real numbers, we would get no solution. The no solution case with and can occur in two instances. So there's two ways with an and problem that we can get no solution. All right. The first way is if your inequality just happens to fail right off the bat. What I mean by that is, consider a problem like this. If I had 9x plus 8 is less than 5 plus 9x, which is less than 10x plus 10. Okay? Just like my previous problems, if I tried to break this apart, no problem. I can do 9x plus 8 is less than 5 plus 9x, right? Just like this. Capture this piece. And I can also do 5 plus 9x is less than 10x plus 10, right? Capture this piece altogether. If I tried to solve this first one, you may already be able to see what's going to happen. If I subtracted 9x to eliminate this plus 9x over here, I'd have to do the same on the left side of the inequality. And we'd end up canceling out our variables and get a false statement. Okay? This is not true, right? 8 is not less than 5, right? So since this inequality just outright fails, this inequality is feeding us lies, it is a liar to us. We don't like that. We would just say right away, the whole problem falls apart. It's like Christmas lights. If one doesn't work, the whole thing doesn't work. And I'd say this has no solution. We don't even have to deal with the second one. All right. You could try to solve the second one. The second one would actually work out just fine. But the fact that we got one inequality of our two that falls apart, again, means the whole thing falls apart, and we just say that there's no solution. All right. The other way that an inequality with and can have no solution is if there's no overlap between the two sections. Notice here and here, we've seen this inequality sort of pointing in opposite directions, giving us overlap. What if, like what happened with an or problem, excuse me, our inequalities pointed away from each other and there was no overlap? Well, if that occurs, then there is no solution. Check this out. I'm going to have negative 2 minus 3x is less than 10 minus 7x, which is less than or equal to negative 8 minus 5x. Right? Just another example here. Last one. I'll split this apart just like before. Consider this first group and this second group. I'm going to say that negative 2 minus 3x is less than 10 minus 7x. And also that 10 minus 7x is less than or equal to negative 8 minus 5x. Okay? If I were to solve out this one, I'll do it pretty quick just for the sake of time. Add 7x to both sides, keep everything positive. Negative 2 plus 4x is less than 10. Add 2 to both sides now. I would get 4x is less than 12. And lastly, divide both sides by 4. We end up with x is less than 3. No problem so far. So far, so good, right? Can do that. If we did the other side, let's see. Let us add 5x to move that to the left. I would get 10 minus 2x is less than or equal to negative 8. Subtracting by 10 on both sides now, we'd get negative 2x is less than or equal to negative 18. That's negative 8 take away 10 more. And last but not least, dividing both sides by negative 2 is going to cause that inequality to flip. So we're going to get x is now greater than or equal to positive 9. Negative 18 divided by negative 2. All right. Take a look at what this looks like on a number line. I'll do it right over here in this little corner. Right? This is x is less than 3. Looks like this. Here's 3. If x is less than 3, you'd have an open circle and go this way. Should have made my arrows a little bit bigger. That's okay. Okay. If I have x is greater than or equal to 9, well, guess what that looks like? Here's 4, 5, 6, 7, 8, 9. I'd have closed circle, and I'd be going this way. Well, is there a region of the graph that's captured by both of these? Are there values for x that are less than 3 and greater than or equal to 9? Can you think of a number that would be less than 3 and also greater than or equal to 9? No, there's no overlap in here at all. This would be great for an OR problem, but for an AND problem, no dice. This has no solution. And that, again, is the case because there's no overlap at all. AND problems, we're looking at the overlap. There is no overlap. So we're out of luck, right? So again, no solution can occur for 2 reasons. Number 1, the inequality can just fail outright, like just doesn't work. We get a false statement, right? A false statement. And the second way we end up with no solution is if there's no overlap. Then there's no values that are going to satisfy both of these at the same time. There's no number, and if you can think of one, then you might be Time Magazine Person of the Year. There's no number that's less than 3 and at the same time greater than or equal to 9. If you think of one, give me a call, let me know. All right. In any case, let's do a quick little recap. What we did today is we talked about compound inequalities involving the word and. When we're dealing with and, we're really looking for the overlap because we're trying to find things that are true for this statement and this statement. Numbers that are less than or equal to 6 and greater than 4 would be in this little section right here. Okay? You can sort of visualize that by doing out your number line inequality separately if you so desire. And then you see like, ooh, this little region is where they overlap. But once you get more and more comfortable, you should be able to just go ahead and sort of picture it in your head, like we did with this example. X is less than 4, open circle shaded this way. X is greater than or equal to 1, closed circle shaded this way. We could see this would be the region between them. Same thing over here. And same thing over here, except with these problems, we saw that, ooh, we could kind of have this little, it's almost like an inequality sandwich. You have one thing sandwiched between the two outsides. And we can just break apart that inequality sandwich to say that this is our first inequality and this is our second inequality. Okay? Second one. First one. And just solve like normal. All right. Last but not least, we talked about problems in which there are no solution. Just happens to, if the inequality just falls apart, where there's a false statement, like we saw with regular old inequalities, or if we end up with no overlap. All right. So that should be a pretty comprehensive explanation for you. I would encourage you to try those practice problems on your own to see how you do. Other than that, we will go over more questions on compound inequalities next week. But that's all I got for you guys today. I hope you have a fantastic rest of your day, and good luck with the compound inequality stuff. Take care.